A huge red-hot metallic sphere about the size of the moon, roughly as hot as the surface of the sun, around 11,000 degrees Fahrenheit. It lies deep beneath our feet, far beyond the reach of any drill, at the very center of the Earth. This is the Earth's core. Its activity drives plate tectonics, generates Earth's magnetic field, and influences life on the surface. For a long time, the inner core was thought to be stable, solid, slowly growing, and rotating almost in step with the planet. However, recent publications challenged the smoothness of this timeline. So what would happen to our world if it began to behave differently, slowing down or even reversing the direction of its motion? Today we'll set off on a journey to the center of the Earth, not literally, but through the eyes of scientists. Why did the inner core remain hidden for so long? And how do earthquakes give us our only opportunity to peer into the core? A major study published recently in the journal Nature reports that the inner core began to slow down as early as 2010. Today, according to numerous analysis, there's a growing evidence that it started to move more slowly than the planet itself, for the first time in decades. Why do these processes deep within the Earth matter for the entire planet, from the magnetic field that protects us to the very length of our day? To make sure everyone's on the same page, let's start with the fact that the Earth is structured like an onion. It has several layers. We live on the crust, a thin, rigid shell only a few dozen miles thick. Beneath it lies the mantle, a vast region of hot, semi-solid rock extending to a depth of about 1,800 miles. But the most extreme layers lie even deeper, the core. The outer core is an ocean of liquid iron and nickel about 1,300 miles thick, scorching hot, and in constant turbulent motion. And at the very center, around 3,200 miles beneath the surface, lies the inner core, a metallic sphere with a radius about 3/4 the size of the moon. The inner core is incredibly small compared to the planet as a whole, making up just 1% of Earth's volume and about 1.5% of its mass. It consists of a solid iron, nickel alloy, compressed under pressures more than 3 million times greater than atmospheric pressure and heated to temperatures of several thousand degrees. Such temperatures are comparable to those found on the surface of the Sun. Despite these extreme conditions, the inner core plays a crucial role in the workings of our planet. It's gravitationally anchored within the molten liquid outer core, and its very presence helps power Earth's geodynamo, the process within the flowing metal of the outer core that generates the planet's magnetic field. In fact, Earth's inner core exists only thanks to a set of very specific chemical processes. Recent research shows that if the core were made of pure iron, it would not be able to solidify without overcooling by nearly 1,800 degrees Fahrenheit, a scenario that could disrupt or even destroy Earth's magnetic field. Fortunately, the core also contains lighter elements, such as carbon. One study found that even about 3.8% carbon in the core alloy would allow it to solidify and form a solid inner core, stabilizing the magnetic field that protects our planet. Yet despite all its importance, the inner core remains inaccessible and mysterious. We cannot drill anywhere near it, and we cannot observe it directly. So how do we know it even exists, and how can we reason about what it's doing? The answers came slowly, through a kind of scientific detective work that unfolded over more than half a century. At the end of the 19th century, scientists were only beginning to understand the structure of Earth's interior. The first breakthrough was made by a German physicist, Emil Weichert, who in 1896 proposed the Earth is not homogeneous, but composed of layers, with a very dense iron core at its center. This was a radical idea at the time, when many believed the planet was made of the same material throughout its depth. Weichert noted that Earth's average density is much higher than that of surface rocks, implying the presence of much heavier material inside. His idea laid the theoretical foundation, and experimental evidence soon followed with the development of seismology, the science of seismic waves. In 1906, British geologist Richard Dixon Oldham, while analyzing seismograph records of earthquakes, noticed that S-waves failed to reach the side of the Earth opposite the epicenter. Since S-waves cannot travel through liquid, he concluded that a liquid layer deep inside the planet was blocking them. Earth's outer core likely composed of molten iron, as Weichert had suggested. In 1913, seismologist Bino Gutenberg precisely determined the depth of the boundary between the mantle and the core, about 2,900 kilometers, by mapping the bending of P waves and the resulting shadow zone. Later in 1926, Harold Jeffreys demonstrated that the core must be liquid, as its rigidity inferred from seismic data was essentially zero. However, a new mystery soon emerged. Weak P waves were occasionally detected within seismic shadow zones where they should not have appeared. After a powerful earthquake in New Zealand in 1929, such signals were reliably recorded on the opposite side of the Earth, drawing the attention of Danish seismologist Inge Lehmann. Lehmann carefully analyzed the data and proposed a bold hypothesis. Perhaps Earth's core itself is layered. She suggested that the wandering P waves were reflecting off a hidden inner core before reaching distant seismographs. In September of 1936, Lehmann published a short but revolutionary paper, P Prime, and she announced the existence of Earth's inner core. Her model elegantly explained the anomalous P waves that appeared where they were not expected, as reflections from the solid inner sphere. At first, her idea was met with skepticism, but further calculations and observations in 1938 and 1939 confirmed Lehmann's conclusions. Definitive proof came in 1971, when the analysis of Earth's free oscillations after major earthquakes showed that the inner core is indeed solid. Nevertheless, the credit for the discovery rightly belongs to Lehmann, who single-handedly revealed the existence of our planet's heart. So, seismologists discovered that some waves disappear, others bend, and some appear where they shouldn't. From these anomalies, the outer core was inferred, and later, the solid inner core. But how do we actually see something located 3,000 miles beneath the Earth's surface? Every time a strong earthquake occurs, it sends out P waves or pressure waves, and S waves, shear waves, that travel through the Earth. These waves behave much like light or sound. They refract when passing through different materials, reflect off boundaries, and S waves, they simply stop when they hit a liquid. By carefully measuring the arrival times of these waves at seismic stations around the world, scientists can deduce that they travel deep inside the Earth. Today we talk about differences in wave arrival times of just 0.05 seconds. And this is over a total travel time through the Earth of around 20 minutes, demonstrating measurement accuracy down to the thousandths of a second. In essence, seismologists use earthquakes as a form of planetary CT scans, creating maps of Earth's internal structures based on the signals that pass through it. Modern seismology has yet another trick up its sleeve: observing repeating seismic events. These can be earthquake doublets, earthquakes of nearly identical magnitude and location occurring a few years apart, or even human-made events, such as underground nuclear tests. The two such events send waves along the same path through the core. Any difference in their recorded signals reveals changes inside the Earth over the time interval between them. In recent years, scientists like Dr. John Vidal from USC and others have compiled catalogs of these repeating seismic sources. They gathered data on 121 recurring earthquakes that occurred between 1991 and 2023, many near the South Sandwich Islands in the Atlantic Ocean. They even included recordings of old Soviet nuclear tests from the early 1970s and other tests, all to obtain pairs of signals traveling through the same section of the inner core with differences spanning several decades. By lining up these seismic twins, researchers can detect incredibly small shifts, the order of fractions of a second in travel time, indicating that something inside the core has changed. But more on that later. The high-precision seismic investigation has opened a window into the behavior of the inner core over time. It was thanks to this approach that in the 1990s, one of the greatest discoveries in Earth science was made. Researchers realized that the inner core is not synchronized with the rest of the planet. It rotates at its own speed. In 1996, seismologists Zidong Song and Paul Richards made headlines by analyzing seismic waves from repeating events and discovering that the inner core rotates roughly half a degree faster than the Earth's mantle and crust. This phenomenon was called superrotation. Essentially, it was found that the inner core completes one extra rotation relative to the Earth's surface approximately every few hundred years. It was a stunning idea. The Earth literally has a planet within a planet, rotating slightly faster than everything above it. At first, not everyone agreed on the details. In the late 1990s and 2000s, additional studies were conducted. Some confirmed the presence of a steady superrotation, but reported different rates. Others began to suggest that the inner core's rotation might be irregular rather than constant. By the 2010s, evidence began to emerge that the inner core's rotation could speed up, slow down, or even oscillate. In fact, studies conducted by research groups in China and the United States detected signs of possible 6-year cycles, small back-and-forth swings linked to subtle periodic changes in the length of the day. The idea was that gravitational forces between the inner core, outer core, and mantle could induce oscillations in the inner core, even temporarily altering its rotation direction every few years. This was a controversial hypothesis, and measuring such a short cycle is extremely challenging. Nevertheless, all scientists agreed on one point: the inner core indeed rotates differently from the rest of the Earth. This rotation is driven by a balance of forces in the core and mantle. The electromagnetic force of the geodynamo pushes it one way, while gravitational interactions with the mantle pull it the other. It's a delicate balance, and when these forces change, so does the rotation. By the early 2020s, seismologists had recorded instances of the inner core accelerating relative to the Earth's surface, as well as periods when it appeared to slow down. But the biggest surprise was still to come. More precise data allowed scientists to actually observe the inner core's rotation stopping and possibly even reversing direction. To say that our understanding of the Earth's inner core has radically changed in the past few years, that would be an understatement. A series of studies conducted between 2023 and 2025 has shown that the planet's iron heart is doing something unexpected. It is slowing down and may even be reversing direction. This news emerged in January 2023 when Dr. Ya Yang and Dr. Zidong Song from Peking University announced astonishing results in the journal Nature Geoscience. They analyzed seismic waves from nearly identical earthquakes dating back to the 1960s and discovered that around 2009, the inner core's rotation had almost stopped. For roughly 10 years after 2009, the travel times of seismic waves, which had previously been changing, became static, indicating that the inner core was no longer gaining speed relative to the mantle. Even more provocatively, Yang and Song noted that this could be the beginning of a reversal process, part of an approximately 70-year oscillation cycle. They suggested that the last major turning point likely occurred in the early 70s, implying that the inner core speeds up and slows down like a pendulum over decades. This rotation has been inferred from temporal changes that should traverse the same path through the inner core, they explained. And now these changes disappeared after 2009. In their view, the inner core may be backtracking on its long journey, oscillating like a slowly swinging compass needle. Just a year later, in 2024, the previously mentioned group led by John Vidal and the University of Southern California published new data that unequivocally confirmed the slowing of the inner core. Using information from repeating earthquakes and even old nuclear test data, Vidal's team observed that the inner core, quote, began to decrease its speed around 2010, moving slower than the Earth's surface. In other words, what had once been superrotation had turned into subrotation. The inner core was now lagging behind the mantle's rotation. From one perspective, one could say the inner core is rotating in the opposite direction. Although it still moves eastward, it simply moves more slowly than the Earth, giving the impression of falling behind. Vidal remarked on the surprising nature of this finding. "When I first saw the seismograms that hinted at this change, I was stumped," he admitted. But when we found 24 more observations signaling the same pattern, the result was inescapable. The inner core had slowed down for the first time in many decades. The irrefutable evidence ended the debate. Something had clearly changed in the core around 2009 or 10, and multiple data sets captured it simultaneously. What could have caused this slowdown? The core is not a clock isolated from the rest of Earth. It's influenced by its surroundings. Vidal and colleagues pointed to interactions between the inner core, the liquid outer core, and the mantle. They proposed that changes in magnetic field forces and the gravitational pull of denser mantle regions can alter the inner core's rotation. Essentially, the push of the geodynamo versus gravitational attraction can vary over decades, leading to acceleration or deceleration of the inner core. In fact, these changes correlate with subtle variations in the length of day and the magnetic field at the surface, suggesting it's all part of a vast interconnected system, from the core to the crust. In 2025, a new discovery revealed that Earth's inner core holds surprises not only in its motion, but also in its structure. The same team led by Vidal found evidence that the surface of the inner core undergoes changes over time. In a paper published in Nature Geoscience, they described unusual seismic waves from repeating earthquakes whose properties had never been observed before. Detailed analysis showed that the cause was a slow deformation of the inner core surface at its boundary with the liquid outer core. The best explanation is that parts of this surface undergo viscous creeping or warping on human timescales. This was unexpected, as geologists had long assumed that the solid metallic inner core remains rigid over short time intervals. The discovery suggests that Earth's deep interior is more dynamic than previously thought. Flows of molten metal can actually reshape the solid core, much like ocean currents shape a coastline. This finding also resolved a long-standing debate. Changes observed in seismic data are linked to both the rotation of the inner core and to physical changes at its surface. However, new questions remain. Is the recent slowdown in core growth the beginning of a new cycle? And how do these processes affect the mantle, the crust, and Earth's climate? So what do we know today? This tiny central sphere, making up only about 1% of the Earth's volume, has a disproportionately large impact on the entire planet. The inner core plays a crucial role in generating the magnetic field. As it slowly grows, it releases heat that drives convection in the outer core, powering the geodynamo. Changes in the rotation or shape of the inner core can influence these processes. Studies by Yang and Song have identified a correlation between the recent slowdown of the inner core, small changes in the magnetic field, and variations in the length of the day. These effects are subtle, on the order of milliseconds and slight magnetic fluctuations, but they indicate that Earth's core and surface are linked through the exchange of angular momentum and magnetic coupling. The formation of the inner core was a turning point in Earth's history. Had it never solidified, the magnetic field might have collapsed millions of years ago, leaving Earth unprotected from cosmic radiation and the solar wind. This protection is what ultimately made the planet's surface habitable. The age of the inner core remains debated. Some scientists argue it's relatively young, 0.5 to 1 billion years, while others, they suggest it's much older, over 2 billion years. Recent discoveries about the core's composition, including the possible role of carbon in triggering solidification, are helping to refine these estimates. Looking ahead, the inner core will continue to grow very slowly, by a few millimeters in radius per year. In the distant future, billions of years from now, its complete solidification could lead to a significant weakening or even the disappearance of Earth's magnetic field, as what happened to Mars long ago. Long before that, however, scientists are investigating whether oscillations of the inner core may be linked to magnetic field cycles, including shifts or even reversals of the magnetic poles. The existence of the inner core was proposed only in 1936. Since then, our knowledge of it has expanded dramatically, though it still holds many, many mysteries. As this video comes to an end, remember that beneath our feet, billions of tons of iron continue to rotate and transform. The heart of our planet, quietly sustaining Earth's stability and life itself.